Today we're going to try to prove the thin lens equation. We've used this equation quite a bit, so we hope that it's correct. We hope that it's a valid equation. Okay, today we're going to go to that step to determine whether or not it is a valid equation. The problem of our activity is going to be, is the thin lens equation valid for a particular converging lens, a particular convex lens? Now, remember, you're going to be testing this with one particular convex lens, and that's why our problem is phrased the way that it is. Even if it does show that it's correct, the results show that it's a valid equation for this lens, that doesn't mean necessarily that it is for every single lens out there. It is, but the proof that we're doing today is simply for one convex lens, the convex lens that you're dealing with today. Is the thin lens equation valid for a particular thin converging lens? This is what the apparatus is going to look like. Every group is going to be given a meter stick. Every group is also going to be given an optics kit. This optics kit is going to consist of a couple of stands that are going to allow you to place the meter stick on the table and not hold the meter stick. So it frees up some hands. Okay, place the meter stick in these holders. Okay, this is holder number 1. Holder number 2 would be over here outside of the picture. Place it on the desk. Okay, also attached to this meter stick is going to be a candle and a candle holder. That's going to serve as our object. We could use something like a pen as our object or an eraser as our object, but we're going to use a lit candle as our object because it generates a lot more light than a pen reflects. So it's a lot easier to see an image of a flame than it is of a pencil or of an eraser. Okay, the pencil and the eraser both reflect light, but not nearly as much as the candle produces itself. So that's going to be our object. You're going to see a convex lens in a convex lens holder right there. And then, and that's attached to the meter stick as well. And then you're going to see a card, which is going to act as your screen in a screen holder. All of these things are able to move back and forth along this meter stick. So what exactly are we going to do? Let's take a look at the variables. What do you think we're going to change? What do you think that we want to manipulate in this experiment? You see the picture at the bottom here. Okay, what are we going to change here? What distance? From the what, sorry? Good, the object distance. From the object to the lens. Now listen real carefully about this, okay? The object distance is not the position of the object. That's not how we define it. The object distance is the distance from the object to the lens. So there's a couple of different ways we can change the object distance. What are they? We can move the object or we can move the lens. It doesn't matter. If we move one of those two things, the object distance will change. I'm suggesting to you that you keep the object, the candle, in the same place at the end of the meter stick, and you move the lens back and forth as necessary. Here's why. This meter stick is obviously a meter long. Sometimes if we put our object way up here, really close to the lens, way up here, then we may run out of meter stick space. The card, the screen, may have to be placed way back here in order to see the image. We want to use as much of the meter stick as we can. We don't want to waste all this space up here. So let's keep the object at the end of the meter stick, and then let's just simply move the lens in order to change the object distance. That allows us to use the entire meter stick instead of wasting this bit at the beginning. All right? So change the object distance, but do it by changing the position of the lens. What's the responding variable going to be? The image distance, right, where the image is relative to the object. Now, how are you going to determine where that is? Well, let's say that I've got my object placed where it is in this diagram. I've got my lens placed where it is in the diagram. My object distance is a certain value right here that we can measure on the meter stick itself. I want you guys to move the card back and forth until you find a good, clear, sharp, focused image of the flame. Now, what should that focused image look like? I got two pictures of kind of images up here on the board right now. The first one, what do you see? You see an upside down flame, right? That's what you should see. No matter where you put the card, you're going to see light going through. Light goes through this lens, whether there's an image formed or not. Even if it's a virtual image, even if it's at the focal point where there is no image formed, there's still going to be light going through the lens, and you're still going to see light on the card. But that's not an image. There's nothing focused about that. So this is not what you want to see. If you see that, then move the card somewhere until you see this. Once you see this, then you're going to measure this distance, the distance from the card to the mirror, the lens, I should say, and you're going to record it as the image distance. So you've got an object distance, you've got an image distance, then what are you going to do? Do it again, right? Do it again. But somebody told me that we're going to change the object distance by moving the lens. So let's move the lens somewhere, get a new object distance, get a new image distance, get another object distance, get another image distance, and so on. You're going to keep repeating it so that you have a total of 10 different trials. Your data table is going to look like this. Object distance, all the way down through 10 trials. Image distance, all the way down through 10 trials. Now, we also need the focal length of this lens. That should be, in fact, the very first thing that you do, find the focal length of the lens. I showed you how to do that in class one day. You guys remember? Anybody remember the procedure we used to find the focal length of the convex lens? No, good guess, but that would work for a mirror. Remember we focused on a far-off object on the condos across the street? When the light rays are coming from the condos across the street, the ones that actually strike the lens are essentially parallel to the principal axis. If they're parallel to the principal axis, then they're going to converge where? At the focal point. So wherever you get a good, clear, sharp, focused image, when you're focusing on something that's far away, like the condos across the street, that's your focal length. Okay, measure that distance. Measure the distance between the screen and the lens when you're focusing on that far-off object. Write that down as your focal length. You should find that it's probably somewhere in the range of 9 to 20 centimeters. So don't look at 50 centimeters, okay? It's going to be somewhere in that range. Okay, it could be outside of that range the tiniest little bit, but not much. So start somewhere in there looking for it. All right, what do you think we're going to do now? Now that we have this nice table of object distance and image distance. We're going to graph it? We are, but we're going to do something to it before we graph it. With your Snell's law activity, we took theta 1 and theta 2 and signed them both, right? Sine theta 1, sine theta 2. Here, we're going to flip them over. So we're going to say not dO and dI, but the inverse of dO and dI. 1 over dO, 1 over dI. If dO was 10, then 1 over dO would be 0.1. If dO, sorry, yeah, no, that's right? If dO was 1, then 1 over dO would be 1. If dO is 5, then 1 over dO would be 0.2. Literally, all you're doing is flipping it over. And you can do that really quickly on your calculator by hitting that x to the minus 1 button, or you could type in your original data table on Excel and have Excel do it for you, as long as you create the formula. Do the same thing with DI. Create a 1 over DI column. Notice the units here. If DO and DI were centimeters, then 1 over DO and 1 over DI would be per centimeters, right? Or centimeters to the minus 1. Then we're going to plot the graph. Now we see a data table. We know we're going to plot a graph. It's just a matter of if we use those variables or we do something with those variables to get what we want. We're going to plot a graph of 1 over DI as a function of 1 over DO. 1 over DI versus 1 over DO. The graph that you're going to get here is going to be in some ways like every graph that you've seen this year, in other ways unlike some of the graphs you've seen this year. It's going to be a straight line, but it's going to be a straight line sloping downwards. Well, we know how to deal with this, right? Every time we see a straight line on a graph, especially if it's a graph we've never seen before, we write down an equation. And the equation for every straight line graph is y is equal to mx plus b. Now let's replace y with whatever's on our y-axis. 1 over di. What's m stand for? Slope, good. X is, the x-axis is 1 over do. Usually we can just scratch off B, the y-intercept, right? Can we scratch it off here? No, there is a y-intercept. If it's sloping downwards, then there has to be a y-intercept here. So we can't get rid of it. It's the first time we've had a problem where we can't get rid of the y-intercept. Now we come up with an equation from our data sheet that has the same variables in there. Which one do we use from our data sheet that has both di and do in it, in the form of 1 over do and 1 over di? Good. 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 1 over f is equal to 1 over do plus 1 over di. Now, what we want to do with this equation from our data sheet is just rearrange it to take the same form as this one. In other words, solve for 1 over di. Let's take the 1 over do over by subtracting. It becomes negative 1 over do plus 1 over f. We could have phrased it as 1 over di is equal to 1 over f subtract 1 over do. But I did it this way because it looks more like my graph equation if I rearrange it this way. If 1 over di, then 1 over do come first. Now we start crossing off things that appear in both. 1 over di, gone. 1 over do, gone. What's left? Well, we have the slope is equal to minus negative 1. Your data will be different than your data, which will be different than your data, which will be different than your data. You will all get a slope of minus 1, no matter what. If you've done this properly, your slope will be minus 1, or at least really, really close to minus 1. Theoretically, it should be exactly minus 1. That's not what we're going to use to prove the thin lens equation is valid. Rather, what we're going to use is the y-intercept. The y-intercept of this graph is 1 over the focal length. So the focal length will therefore be 1 over the y-intercept. So calculate the focal length. Why would we do that? Why would we calculate it? We already measured the y-intercept. We already measured the focal length, right? Why would we try to calculate it here? Well, we made an assumption here. When we did this analysis, we assumed that this equation is valid. If the value we calculate with our assumption ends up being the same as the value that we measured, then our assumption must have been correct. If the value that we calculated making that assumption is different than the value we measured, then our assumption was incorrect. All right? Go ahead. Yeah, our rule of thumb is 10%. So if you're within 10%, you're good. Yeah, you're good there. Yeah, it's probably a good idea there. I mean, if you're right on, then it doesn't really matter, right? But if you're off by a little bit, it's probably a good idea to do a percent difference to see how far you're off. Okay. If one is 0.3 and the other is 68,000, well then, no, it wasn't verified. But if you're not sure by looking at it, then you'd probably have to do a percent difference. Probably not a bad idea, anyways.
So how can we calculate a percent difference? Would you like to do this in the lab? So like do a conclusion?
Yeah, I'll show you that in a second. So you've just verified or refuted the thin lens equation. Let's conclude. Let's conclude whether it's valid or not, and then let's put in some sources of error. Now, what do we have to hand in for this? It's not a full lab write-up, but it is a little bit more than the last one you did. I want you to hand in a problem, the variables, and we can skip forward to data, analysis, conclusion, and sources of error. I could make you do a procedure here, but in the end, I gave you the procedure, which we almost always do anyways, but save a little bit of time here, avoid that, and just do problem, variables, data, analysis, conclusion, and sources of error.